This is Paul Johnson, and today we're going to talk about the new frontier of transforming the energy industry. Dr. Matthew Mehmet, who is a Ph.D., is here with us today, and we're going to talk about a variety of things going on in the nuclear space. Now, Dr. Mehmet is a Ph.D. in nuclear science and engineering from MIT. He also has an MS in nuclear science and engineering from MIT before that, and a BS in chemical engineering. He has a wide breadth of knowledge, and he's focused on a new company, Alpha Tech Research Corporation. This new company is looking at transforming the industry. We're going to talk about a wide variety of issues that are challenges, specifically in the supply chain that leads up to these new modular facilities actually being able to work. What has to happen in transportation as well as material development, especially with Russia coming offline, the regulatory needs of the industry, and then also talking about how this new technology that is a very different technology than what you see in the existing nuclear facilities is not only safer, but it is dramatically cheaper and much easier to be able to help build out this new economy. We will be very dependent in this new economy on energy resources, not only to provide for the economic development needs of our communities as things like AI technology, blockchain technologies, driverless cars that are electric all begin to come on the road. The estimates are that we'll grow by 10 times our need, but also making certain that the people who are the poorest in our community are able to participate. We've got two great PhDs who are going to be on this program with us today talking about this subject. And I'm just kind of an ordinary guy who's optimistic about America and believes that the U.S. is still a cause for good. But if you like this topic, press that subscribe button. Let's get on with this show and learn something today.
Destiny. Destiny. You and I have a rendezvous with destiny. 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 You and I have a rendezvous with destiny.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Well, Matthew, I'd like to welcome you to the New Frontiers program today.
Thanks. It's great to be here.
And Professor Thompson, I'd like to welcome you back as well. Thanks for being here today.
Thanks, Paul. Great to be here and to meet Matthew. I'm really excited about the conversation.
Yeah, you can tell with that accent, Matthew. I like calling him Lord Henry. I mean, he just has that.
You've never called me that before.
Well, you know, they used to call me Lord Mayor. I can't tell you how many people when I was mayor that would say, "Lord Mayor, please don't do that." So, okay, so here's the thing.
I love it.
I have Henry has a lot of experience in this. I'm a politician and a CEO. So I'm going to start with telling you that if you're a really good politician or CEO, you need about a size 48 chest, size 2 hat. All right. So I'm going to ask all the dumb questions today and ask for your forgiveness as I'm doing that. But what I'd like to start with is the real basic question. The amount of effort that you have put into this throughout your entire life. Help me build the case for our people that are watching as to why nuclear is even important. Why is it important from an environmental standpoint? Why is it important from a poverty and a cost standpoint? And why is it important from us to be able to meet our future in energy needs?
Right. So thanks. Great question. Really, when it comes down to it, quality of life, standard of living comes down to power, to electricity. And when you see the first world countries and the countries that have high success, high affluence, high happiness metrics, often they have easy availability to electricity. And right now, the U.S. has almost all that we could use electricity supply. And it comes from a variety of sources: fossil fuels, renewables, nuclear, hydroelectric. The challenge is that some of these sources of electricity, notably fossil fuels, are beginning to be a little more undesirable to the general public as we are concerned about environmental pollution. When we talk about SOx and NOx and global warming and emissions and things like that, the general public is kind of losing their appetite for burning things. And there are ways to make those concerns go away, but it does increase the cost. For example, I have a colleague here at BYU who does carbon capture and oxy-coal combustion. And with those two technologies together, you can get rid of most of the pollution of coal plants. The question is, how much are you willing to pay for that? Because it does increase the cost of that power. Renewables are a fantastic option that we have tapped in certain areas where they make sense. Where the wind blows is a great place to have windmills. Where you have a lot of sun, like Arizona, is a great place to have solar. But they have their own challenges. Primarily, the availability and the timing of that power is not conducive to when we use power. A lot of people like to talk about sizes of power plants. This power plant is so many megawatts. Well, there's another factor, and that is how often and at what times can you produce that power? And we don't have any control over renewables and when that power is produced. And in fact, historical trends and experience in California has shown us that oftentimes the times that the sun is shining and that the wind is blowing are not the times when people are using the most power. When you come home from work and you want to relax and you turn on the TV and you start cooking dinner, that's when we start jumping up our electricity use. That's the same time that the wind is cutting off and that the sun is going down. We don't have that power production. And a lot of people have proposed batteries. But in order to have the number of batteries we need to keep renewable electricity online around the clock year round is staggering. And we, quite frankly, probably don't have lithium supplies to supply that many batteries with the current technology of batteries. The thing that's really nice about nuclear is it is probably the very best of anything at making heat and thus electricity. It's 10 million times more effective at making heat than burning things. And so we just get a massive amount of energy out of a very small amount of fuel. And the process of making this heat doesn't release any gaseous emissions at all. So the pollution that you will see is really reduced to the nuclear waste. Now, there's been challenges to nuclear that we have faced over the last several decades that have kind of made people leery, whether they're real or perceived, about the use of nuclear energy. And it really comes down to four main challenges. One is the nuclear waste. Everybody's worried about it. What do we do with it? We hear that it lasts forever. One is nuclear safety. We have a lot of fear because we have things like the Fukushima event, the Chernobyl event, the 3 Mile Island accident, where we are hearing about these awful, awful things and the devastation and the cost. And so people are concerned about safety. We're worried about weapons, because anything that can be used to make heat can also be used to make a weapon. And we're worried about cost, because recently we get the story and we've seen the evidence that nuclear power plants are very expensive to build. And so the benefit of nuclear is that it provides a massive amount of energy. The challenge is those four cardinal issues, whether they're real or perceived, need to be addressed. And those are largely a result of the type of technology we selected back in the day, where we had an option of multiple different plants. We chose the light water reactor because it had been proven in subs and ships, and Rickover was very persuasive. Admiral Rickover was the one who advocated moving those sub reactors to land. And so we chose this light water reactor. And for another reason, it was very good at making weapons material. And back in the 50s, 60s, the US was really interested in making a lot of nuclear weapons. And so a way to make a lot of nuclear weapons material was desirable. And so what we have now is a challenge of deciding what source to use to make electricity, and it's exacerbated by this AI revolution that we're understanding is happening now. This data need, this requirement for processing huge amounts of data, anticipates an increase of the current electricity demand by up to 5 times. And then when you throw on electrification of transportation, you're talking about anywhere from doubling to increasing by another 5 times. So we're talking about a massive increase in electricity demand in the coming decades. And we haven't built new plants in the US for a very long time. And here we're expected to increase that capacity by 5 to 10 times. That's going to be a huge ask, period, from the construction and the capital standpoint. But when we talk about the power that produces little emissions and is reliable, there's really only one choice that fits that bill, and that's nuclear. And so the question is raised, can we address the other issues so that we can have no emissions, no waste, no safety risk, but the large amounts of power that we're going to need over the next decade? Because multiplying by even a factor of 2 is a huge ask. It's been decades since we've had to fill out that much power in the US.
Right. So before we go on, let's talk just for a moment about those energy needs that you were talking about. The digital needs are one major component of it. You spoke about the fact that we have AI technology, but we also have huge potential with blockchain technologies, which are massive consumers of energy. And then on the other side, we have a lot of people who are moving to electric vehicles. Now, what I find with an electric vehicle, it's funny how many people will tell me, well, did you really get an electric vehicle to save the environment? The answer is no, I got an electric vehicle because it's a really good car. It's in a lot of ways better than the combustion engine car that I had before. There's less maintenance, less work. I charge it up inside my home. It's incredibly convenient. And that says to me there are probably a lot more people that are going to be looking to buy those cars, placing a demand back on the grid. All of those things, you're saying a 10 times increase. Is that a 10 times increase from the amount of energy that we use today? And over how many years are you projecting that that begins to take place?
So yeah, that would be 10 times what we have now, which is just an astronomically large number, one that we're not comfortable with or familiar with. And we've had our infrastructure up for so long, we don't even comprehend, I think, what that means. And so we're talking terawatts of electricity, and the extrapolation really scales with how quickly you want to make these changes. We have data centers right now begging for more electricity so they can run their blockchain, their AI, their other operations. And what they are being told, based on my conversations with a lot of these blockchain experts and owners, is that they have a delay of up to 4 years just to get the power they're ordering. So they ask for 100 megawatts to run their data center, and 4 years later they might get that 100 megawatts. And so they just can't get power fast enough from a utility, and so they're desperately looking anywhere they can for any kind of source of electricity, even if that means they're going to have their own in-house electricity production. And so when you say the scale or the timing of that scale up, it really depends on how quickly we want to implement these technologies. The technologies are limited by the power, not the other way around.
Yeah, we're seeing that in other fields. I'm in the healthcare industry, but I've also invested quite a bit in real estate, and a lot of the new projects now they're starting to see some pushback that's coming from the utility companies. Now, if you would, before we go into a whole series of questions, help us understand the technology. I know that there's a difference between the saltwater project, or excuse me, the salt project type technology you utilize and what is currently utilized. You're also focused on a distributive model with small facilities as opposed to large. But help us understand that entire field. What's going on in that space? What is it that the company that you're involved with is doing, and what have you seen from your academic research?
Sure, that's a big question, but I'll tackle it as well as I can. And if I miss something, go ahead and ask a follow up. So, in essence, when we talk about nuclear power, it's really quite simple. What we're doing is we're splitting uranium atoms. And what that does is it generates a massive amount of heat, and those leftover pieces of the atom make two new elements. And so we're turning uranium into two different elements and releasing a huge amount of heat. And so back in the 50s, what we did is we tried to pioneer and explore how we could use that heat to produce electricity. And what we came up with something very similar to coal plants, whereas coal plants, you're burning coal dust to make that heat. Now you're splitting the atoms. And similarly, what we did is we decided to run water past solid fuel. So we have this solid fuel and we've encased it in a metal cladding that keeps everything contained inside the fuel rod. And then those heat up as the uranium splits. And they contain those leftover atoms, and the water goes past those fuel rods and it heats up really hot. And then you have a heat exchanger that boils another loop of water into steam. That turns a turbine, and that makes electricity. So it's just like coal power, except instead of burning coal, you're splitting uranium atoms. And we explored a lot of ways to do this, one of them being this water reactor. The problem is because water boils at 100 degrees C, but to make electricity, you want really high temperatures to get better efficiency. We ended up making these reactors at really high pressure. And so these light water nuclear reactors have a really high pressure, and you're dumping a huge amount of heat into the water. And one of the challenges of nuclear power is even when you shut off the fissions, if you put in control rods and stop that splitting of the atoms, those leftover pieces, those new elements, a lot of them are radioactive, and they're going to keep making heat basically forever. And it starts with, about 6% of full power heat. And then over the course of a day, it drops to less than 1%. And then for a long, long time, you're making a little bit of heat. And it doesn't sound like a lot to have a little residual 1% of heat. But if we're talking 1,000 megawatt plant, that's a lot of leftover heat. And so if we don't get rid of that heat, you will heat up the water that's already at high pressure. That raises the pressure more. And then you end up with this problem of how do we keep this thing safe, because you're dumping heat in the water constantly if there's not a way to cool it off. And so when we look at the reactor like Fukushima, which was a light water reactor, the earthquake happened and all those reactors successfully shut down. They put the control rods in, fission stopped. But that leftover heat, they call it decay heat from those radioactive pieces of uranium, kept coming off, and the tsunami wiped out their diesel generators. And when it wiped out their diesel generators, there was no longer any way to keep those reactors cool. There was no circulating flow to remove that heat. So that heat built up and the temperature raised until it melted the fuel. And that's what people worry about. So these light water reactors have a solid fuel. They're cooled by water, but because they're at high pressure, because there's a lot of heat involved, there's a lot of scenarios where you could not effectively cool that fuel and result in this meltdown scenario, which is a problem because then you're releasing those radioactive particles from the fuel because you've melted down the clad that holds that fuel in place. And so over the decades, what's happened is this light water reactor, which we chose, as I mentioned, because it was deemed the most reasonable and the most proven technology, a lot of additional systems and a lot of additional safety procedures have been added over time to make sure that in all possible scenarios, these reactors stay safe. And what's happened is great success. When you look at the deaths per terawatt hour of electricity produced per year in the United States, nuclear is at the very bottom. They are the safest. They trade spots with solar back and forth, but those two end up as the safest power production in the United States, hands down. And the flip side to that expenditure of funds for these light water reactors is that means the more safety systems you add, the more expensive they get. So it's also become a much more expensive form of power because the capital cost of building the reactor, but then all these dozens and dozens of safety systems has gotten quite high. When we talk about some of these advanced reactors, there were other ideas that were proposed for utilizing this nuclear fission process, but they weren't seen as A, as reliable, B, as feasible, or C, as known as the water. Nonetheless, people continue to explore and look at them. And one of the alternatives that was actually explored simultaneously to the water is what's called a molten salt reactor. Whereas the light water was kind of pioneered by Admiral Rickover and the Navy, the molten salt reactor was pioneered by Oak Ridge National Lab. Alvin Weinberg headed up that effort. And in essence, instead of taking this uranium and making it a solid fuel rod that you then encased in mechanical containment and then flowed a coolant past, they dissolved uranium directly into a salt that was melted. Now, why a salt? Well, it turns out a salt, by definition, is a compound that has really strong positive charges and really strong negative charges. And when it melts, those charges dissociate, and you end up having inside this molten salt a lot of charges that, in essence, what it does is it binds everything to them. So when you dissolve something in the salt, it will bind tightly to whatever is dissolving in that salt and stay there. And so they dissolved uranium directly in this salt, and the salt bound to the uranium and trapped it in. And when the uranium splits and forms new elements, it's also trapped in. So in essence, it does the same thing that you're doing with other reactors, but chemically instead of mechanically. In other words, these chemical bonds will trap the fuel and all the waste in, and there is no release. It doesn't let go of them. There's no meltdown scenario where you're going to be releasing these radionuclide particles. And so it's a much, much safer, much less safety-focused design, because inherently it is really quite impossible for these particles to be released. If you were to have a Fukushima type event where, you were to have an earthquake and then floods, what would happen is the salt, because it melts at such a high temperature, it would actually freeze in place. And although decay heat is building up, it's not enough to be able to remelt the salt. And so you have a totally safe concept where if you were to have the worst accidents ever, in fact, we even did an analysis for the military where we looked at what would happen if somebody struck this reactor directly with a missile. and you would spray salt out and it would freeze before it hit the ground, kind of like those YouTube videos where people are spraying boiling water from their balcony and it's frozen by the time it hits the ground. It'd freeze, trap all the radionuclides in place and land on the ground, and you go with a lead light vacuum and vacuum it up and your accident's over. And the difference there is you're having this water at high pressure, high temperature versus the salt that's at atmospheric pressure and that wants to be frozen, and we're actually pushing it out of its natural condition and heating it up extra in order to keep it liquid. And so the accident just looks very different. And there's other advanced reactors as well that also use a solid fuel but use different coolants. When you hear about TerraPower or Bill Gates's company, they're using a liquid metal to cool the solid fuel, because then you get a little bit better heat transfer, you get a little bit better characteristics and efficiency, and in essence, what you can do is burn up used nuclear waste if you put it back in one of these sodium-cooled reactors.
Is Gates reactor is it a light water or is it a molten salt reactor?
Neither one. It's actually a liquid sodium or a metal-cooled reactor. And so the U.S. actually experimented with that right after the light water reactors and started building one. We were building one at Clinch River back in the early 80s, but it ended up getting too expensive and was canceled when it was about 83% done, I believe is the number. And the reason why they followed up with the sodium reactors are also solid fuel, cooled by the liquid metal sodium, but they are really, really good at taking light water reactor waste and burning the most long-lived stuff from it. So in other words, when you have nuclear waste, you really have three parts. You end up with the leftover fuel that didn't burn, and believe it or not, 95% of the fuel doesn't burn. We don't keep it long enough. You end up with what we call transuranics. In other words, uranium that doesn't split when it absorbs a neutron but doesn't split, it will actually transform into new heavier elements like plutonium, americium, curium, and those will slowly build up. And then you have the third piece, which is those leftover split halves of the uranium atom. And so with those three parts of nuclear waste, the one that's really problematic is those transuranics. They're the ones that are radioactive for 300,000 years. They're not really useful for a lot of other things. They're big and they're radioactive. And sodium reactors are what we call fast reactors, and those are very good at taking all those transuranics and splitting all of them, so you don't have much left. So then all you're left with is these leftover halves that they call fission products. And by the way, they're only radioactive for about 300 years. And a lot of those elements that are produced from splitting the uranium are very, very valuable. For example, medical isotopes like moly-99 only come from splitting uranium. We use 20 million procedures a year worth of those isotopes in the US alone, because we use them to image the inside of the body. They'll give you an injection with these medical isotopes, and basically it's like an inside-out x-ray. After a certain amount of time, they'll give gamma waves out, and if they have the film there or a computer there to assess that radiation, they get an inside-out picture of what your pulmonary system looks like, or your brain, or a variety of things. So we use 20 million procedures worth of these isotopes a year. We don't make them in the US. We have to import them from other countries that currently harvest that isotope from the nuclear waste. And that moly-99 is one of many, and that alone is worth about $30 million a gram. And so you have some real value in these leftover split atom pieces. But the question is, how do you harvest it? And with these solid fuel reactors, it's really hard to get that out. But the sodium reactor that Bill Gates is doing would burn up the transuranics and would leave the fission products, so that if somebody was clever and ambitious, they could figure out how to go pull those pieces out and sell them.
How does the molten salt reactor also give you these isotopes?
Yep, any fission will do that. The advantage of the molten salt, and what we were really excited about discovering here at BYU, is we found out that if you were to dissolve that uranium in the salt, once it splits, those two new particles are also bound by the salt and trapped. However, because it's an ionic liquid, those strong negative and positive charges exist. If we stick two electrodes in, depending on the current and the voltage that we run across those electrodes, we can plate out very specific elements, and only those elements. And so without having to go in and chop up fuel and dissolve an acid and do all these mechanical processes you'd have to do for current nuclear fuel, which makes recycling technically viable, but economically not realistic. Now we can simply plate out one by one individual fission products and separate and sell them all, because all of them have a price tag. We're talking about this moly-99 and cobalt-60 and gold and platinum and zirconium and a whole bunch of valuable things. The challenge is in typical solid fuel rods, separating them is hard. But in a salt, it's just a matter of running the right current at the right voltage, and you can pull them all out and separate and sell them. So for the first time, we have a reactor concept where, in theory, you can have zero waste, because this nuclear waste can be separated and sold, kind of taking inspiration from the oil industry, where originally they wanted the kerosene to replace the whale blubber. And eventually we figured out how to use every piece of that oil down to the heavy wax crudes that we use for Vaseline and asphalt, etc. And we applied that same thinking to nuclear waste using the salt reactor, where separation is much more viable, and we can get rid of and sell everything, so there is literally nothing left to the nuclear waste except for these transuranics. Now, you might have heard people talking about thorium. Thorium is an alternative to using uranium, and the advantage of using thorium is you don't make those transuranics in the first place, so you have a truly zero waste nuclear reactor, which is pretty incredible if you think about it.
Is there a difference in the energy use between creating electricity and then the heat that you get actually from the salts, the heat that remains in the salt? Can you explain that to me?
Right. So when you're doing this fission, you're generally making heat. And with a salt, because it doesn't boil at atmospheric pressure, rather you have to get up to about 1500 degrees C, depending on the salt, before it'll boil. So you get really, really high temperatures, and that's a pretty significant advantage, because now you generate this heat and it comes out at about 750 C, and you take that heat to make electricity, and you make as much electricity as you can. And by the time you're done making that electricity, the salt is still at like 650 degrees C, still very, very high temperature. But you've extracted via thermodynamics the most electricity out that you can. There's limits to how much electricity you can pull from heat. And once you're at that 650, you can now use all the rest of that heat for other processes like desalination or like chemical processing, or any of these many manufacturing processes that we have in the US that require high temperatures. You can use this leftover heat after you've made the electricity and almost have a cogeneration plant where you're making electricity and heat at the same time. And by the way, if it's a salt reactor, you can also pull out those valuable isotopes and sell them. And so we've gone from a reactor that has to be at high pressure and high temperature and carefully monitored to one that doesn't require the same level of safety, and that has three different products: the electricity, the heat, and the isotopes. And so the economics look far, far better for a reactor like this, as long as you're not making solid fuel and banking on really, really precise manufacturing, which does not need to be done.
Henry, I've been hogging this big brain all to myself, but I'll let you ask some questions and give some comments if you'd like.
Yeah, Matthew, you keep describing these liquid salt reactors, but I'm wondering, do you actually have one in operation? I remember I saw some sketches in one of your presentations. Are they at an operational stage, or is this still sort of experimental research?
I wish. It would be great if we had one. It's actually beyond experimental research, because Oak Ridge built and operated one for off and on for a decade almost. So we know it works. It's been done. It worked beautifully well. There were, of course, some challenges, as there are with any machines, but they really proved the concept nicely. The reason why we don't have one is not technical infeasibility. It's because of the primary barrier to entry for all things nuclear, and that is the regulatory space. In essence, there's a long history that we don't need to get into, but more or less the worry and fear about nuclear accidents has made its way into the regulatory space, such that, in essence, what the regulator is asking you to do is to prove that your reactor will be absolutely safe in all conditions, but by the way, you can't build it. And so what ends up happening is you have a whole team of engineers and technicians and smart people that get together and over the course of 20 years run experiments and do calculations and look at different pieces of the reactor that they're allowed to build. And then they have to bring those pieces together and justify to the regulator that this represents a real reactor and that it will be safe. And then there's a back and forth between this team and the regulators that, as I said, lasts about 20 years and on average has cost about $1 billion. There's right now two companies that have gone through this process: Westinghouse Electric Company with their AP1000 and NuScale with their small modular water-cooled reactor. And both of them have had significant financial duress after that process. Westinghouse ended up going bankrupt, and NuScale is now struggling with prices and losing customers because of the cost of this licensing process. So the barrier to entry is licensing. And to make things even more complicated, the NRC really only knows how to license a light water reactor because they've had 60 years of experience. And so to come to them and say, hey, we have this new reactor, this sodium-cooled reactor, or we have this new reactor, this molten salt reactor, they lack the manpower and the expertise and the legal precedent to know how to do that. And so the challenge and the difficulty of seeing any of these really cool, neat nuclear ideas that we've been talking about for the last 20 years is to get them through that licensing process. Because $1 billion is such a substantial amount of capital, not even for a product, just for a license, that there are very few players who can play that game.
What about overseas? It strikes me that the story you told about the adoption of the light water reactor was based in the US, but it seems like other countries, even the Soviet Union, followed a similar path. Why haven't we seen these other reactors developed in other countries? Is it easier maybe to do it now? Is there a country that allows for more experimentation in these things right now?
Great question. And yes, the answer is yes. And the challenge is collaboration between countries on nuclear topics is very difficult. The US has a policy that you can't even collaborate with these countries unless they have signed a 1, 2, 3 nuclear collaboration agreement. In essence, it's a political agreement between heads of state or Congress and a head of state that indicates that that country will not try and do anything with the leftover isotopes and that it will not try and weaponize anything. And that's a pretty slim list of countries. You can Google 1, 2, 3 agreement countries and you can get the list. I believe it's around 40 or so, if I remember correctly, of countries you can even work with in the first place. And then there are challenges of export control laws because of the fact that nuclear is a sensitive topic. Having any IP released to other countries is prone to a massive mountain of export control requirements. And so it's almost like you can pick your poison. In fact, Bill Gates's company initially was intending to license and commercialize in China. And they had a pathway planned out. They were in the middle of going through that process. And then China was caught stealing nuclear secrets and doing illicit things with them. And Gates's company was told, sorry, you're going to have to do something else. And they had to pivot and rebrand and refocus to license in the US. And so those pathways are possible. And some countries have better licensing pathways than we do here. But going from the US to them is a challenge. You can either go through heavy licensing regulation domestically, or you can go through the heavy restrictions on export technology and nuclear restrictions internationally. Now, other countries are working on developing these reactors. China has been working very hard on getting a thorium molten salt reactor up and going. They're not really forthright about where things are. They keep telling everybody everything's going fine, but we haven't seen that yet. They're in essence taking that molten salt reactor experiment from Oak Ridge and scaling that up and making their own version. Whereas in reality, with the advances we've made in controls and in materials and in a few other key areas, there are some innovations that can be applied to molten salt reactors to make them better and more reliable and simpler to work, which hasn't yet percolated to some of these other countries. Some of these other countries, such as France and Japan, have actually run sodium fast reactors. Japan has ran a commercial sodium reactor called Monju. There was a sodium fire because sodium is really reactive if it is exposed to air or water. And so there was a leak in one of the pipes and that started a big sodium fire. And since then it's struggled to maintain operation. France had some experimental sodium reactors called Phoenix and Super Phoenix and did some great experiments there, but hasn't really been commercialized. The only country that really operates sodium reactors consistently, continuously is Russia. And they have the Bor 600 reactor that's been operating, I think, near continuously for the last couple decades. As for challenges or problems, we don't really know because Russia is not exactly the most communicative person when it comes to problems and challenges with their reactors and their power sources. But the answer to the question is it's almost like a space race. Most countries are looking at developing nuclear of one type or another, either the traditional light water reactor or one of these advanced reactors. And it's a heavy race technologically, politically, and regulatorily to try and get these things working.
I'd like to focus just for a moment on this this distributive model as opposed to a model that is very centralized. When I was mayor, we were building a plant called the Palo Verde plant, which is a nuclear power plant in Phoenix. Thank God we did, by the way, because we'd be heavily dependent upon coal today had that plant not have been built. There was a lot of controversy around it. One of the jokes that I told during an introduction of somebody from APS was this was a crazy place to build a nuclear power plant, because if it blew up in Phoenix, we wouldn't know it for months. We'd just be walking around saying, "Oh my God, it's 500 degrees outside." But the point was, we had a submarine, the USS Phoenix, that I was able to go out to, which was a nuclear submarine. And I remember the captain taking me to the back of the boat during the time that we were submerged, and there was like this yellow line on the ground. He says, "You can't go past that yellow line." I said, "Well, why is that?" He goes, "Well, that's where the nuclear reactor is. And if you go past it, literally, we can't let you come back until we get back to shore, and it becomes a big, huge deal." But I was amazed that, like, I could see the reactor was right there working in front of us. And it was not this big, huge facilities like I would think about with Palo Verde. So regardless of whether it's freshwater or saltwater, can you talk to me about I'm sorry, the cold water reactors versus the molten salton reactor? Can you tell me the advantages and disadvantages to a distributive model where you're building small plants as opposed to building large plants?
Sure, sure. Yeah, great question. And in fact, really the origins of the large reactor came from cost issues. As we started to add more and more of these safety requirements, they got more and more expensive. So to offset that cost, we started leaning into the economy of scale. In other words, whether or not the plant was 1,000 gigawatts or 10 gigawatts, the monitoring system was going to be the same. It was going to be $100 million. And so if we made it bigger, that meant that $100 million was less of a penalty per kilowatt hour of electricity produced. And so we started making these bigger and bigger plants because that made cheaper cost per kilowatt hour electricity. And that was really where the nuclear industry headed, to try and offset the cost of these increasingly stringent safety requirements. And as a result, that's kind of where the mentality of the industry is, these big monolithic plants that you see for Palo Verde and Diablo Canyon and everywhere else. Well, when I was at Westinghouse, we actually had a potential customer, a utility, come in and have a meeting with us about future reactors. And he said to us, "Look, I appreciate all your effort in making these big, huge reactors that will have centralized power. They work great for us, but they're so expensive. The capital expenditure is so large that we'd have to sell the farm in order to build one. And then there's a risk of waiting for it to be ready to produce power. We just can't handle that kind of risk. So we're likely not ever going to buy a large reactor ever again." And so that got me thinking that really what we need to do is to adapt to the current situation and look at possibility for distributed power. Then we're fighting against the economy of scale, however. And so what we did is we leaned into the economy of mass production. If you can make something in a factory and make lots of those things in a factory consistently, not only will you have more expertise and more familiarity with the process, unlike building one or two giant reactors, but you'll also have a lower cost as you have an assembly line type production of these reactors. Now, on the flip side, that means instead of having a centralized utility that's distributing power, you're going to have a small reactor that you can place in a lot of different areas. And there's actually some real advantages to that. When we look at rural areas or even international locations, the domestic or the distributed model makes a lot more sense, because a lot of them just can't support or facilitate a large reactor. Let me give you an example. We went to the Philippines a couple of years back, and right now they're looking at nuclear power because their only means of producing power is coal. They get the coal from Indonesia. It's very expensive, and it's these large plants that they can't really use to the full extent because they can't get the power to all of their different islands. And so a lot of capital is wasted to get a large reactor, a large coal plant, and they just can't utilize it. And so talking to them and expressing the idea of having one reactor per island at a smaller size, they were really interested in that idea, because rather than buying a 1,000 megawatt plant that they're going to use 300 megawatts for now of, and maybe scale up in the future, now each island can have exactly what it needs. They don't have to worry about crossing the islands in a heavily monsoon-ridden and seismic potentially susceptible area. And it just made a lot more sense to have this distributed power. Even domestically, you see a lot of these small towns in the US, and in order to service these small towns, we need this massive, extensive grid that poses kind of a security hazard, because if something happens to that grid and the grid goes down, you have large swaths of the country that no longer have power. And our grid is not terribly robust. There's a lot of weakness and a lot of dependencies and a lot of back and forth that could cause outages and problems, where a lot of that goes away if we just have power produced right where it's consumed with this distributed model. And so the challenge is, rather than relying on economy of scale, a new model has to be developed, i.e. economy of mass production, which is somewhat foreign to the nuclear industry at this point. But the advantage is it's a much more secure, robust, and much more catered to the needs of the customer power source, where they can buy one of these reactors if they're a small town, or if they're a data center, they can buy 10 to 100 of these and site them at the same spot and get the same amount of power as a large plant. But you're not forced to do just the large plant. The challenge with this utility I mentioned is they were a small utility, and getting 1,000 megawatt plant was just too much. But if they could get 10 megawatts and start making money on the 10 megawatts and then get 10 more and then get 10 more, they could grow commensurately and didn't have to make such a huge upfront capital expenditure that would put a lot of their solvency at risk.
Well, I have a related question if I can.
Please.
Matthew, this raises a question for me that I've been wondering about how nuclear interacts with other power sources, because you mentioned this problem of location and of scale, which I think is really interesting and important. But there's another problem of timing. You mentioned that renewables have this problem with timing. With wind, it's really unpredictable. With solar, even in a state like Arizona, it's going to ebb and flow with the sunlight hours. And as the sun is going down, we are, turning on our TVs, our stoves, our air conditioners still have to run into the evening, and it just doesn't work. Now, my understanding is that nuclear power tends to just run 24 hours a day. You said this Russian reactor, just as an example, has been running for decades constantly. And so it's good for sort of base load that always is there, but it's not as good for peaks and troughs. Now, that suggests to me that, in fact, what we need is not nuclear plus the renewables that we already have, which we still have this problem with timing, but that what we need is nuclear plus some source that can be turned on and off, whether that's a hydroelectric plant where you just start releasing water, or whether it's gas that you just start burning gas, or coal that you just start burning coal. Is this part of the resistance to nuclear, that it doesn't fit with a mix with renewables, where there is so much political commitment to renewables that it's almost like they want to reverse engineer a situation where renewables are a big part of the mix, whether they have to invent new batteries or run cables through the Apache reservation in eastern Arizona through archaeological sites, or whatever they have to do, they're going to do it if they can get the renewables to be in the mix, because the political commitment is to renewables. And because nuclear, it provides baseload capacity, and it doesn't compensate for the timing problem of renewables. Is that part of the problem? So I guess there are two parts to my question. A, is that true about nuclear power, that it runs all the time, provides baseload? And B, does that actually make it incompatible with the renewables that we have?
Great questions, and let me tackle them one at a time, if you will. For the first question, the answer is yes, for a couple of reasons. Traditional nuclear light water reactors and even some of the other solid fuel reactors do not load follow well. And there are two reasons for that. First is the capital cost is so high that you're going to want to make power as much as possible, as constantly as possible, to recoup that cost. But there's actually a second, more pernicious challenge, and that is the fact that if you raise and lower the power of your nuclear fuel, it actually degrades your fuel faster. And so you're actually eliminating your ability to generate power at a faster rate. You're burning that fuel faster, you can think of it as, is if you're adjusting the power level. And in fact, when I was at Westinghouse again, that another utility came and said, look, we're being told we have to shut down our nuclear reactor when the wind comes online, or we'll face a 19 cents per kilowatt hour penalty. And it was a significant challenge. And so, touching a little bit on your second question, that is something that the nuclear industry is aware of and has been grappling with potential solutions. And a lot of people have come up with really brilliant ideas. The first that I would like to highlight is actually Bill Gates. What they're doing is they have that sodium-cooled reactor, as I mentioned. But then what they do is they actually get a giant tank of molten salt that they co-locate with their reactor, so that they run their reactor all day, every day, 24/7 as base load. But to accommodate the peaks and troughs of demand, they will actually send excess heat. Instead of making it to electricity, they'll send it to heat up this salt and to increase the temperature of the salt. And then at times where more power is demanded, they'll draw from the reactor and from this salt that is hotter. They call it a thermal battery, and they'll make more electricity.
So the salt's like a battery, right?
It is. It is a thermal battery is what they refer to it as. So that's one possible solution. Here's another reason where after working on every kind of reactor there is, my love and passion has come to the salt reactor. Just the way that salt reactor works, because it's not a solid fuel, it doesn't damage the fuel to change power level. In fact, all you have to do is change the flow rate of the coolant to the turbine, and it will change the power automatically. So these salt reactors actually load follow really, really, really well. And that transforms nuclear from a base load only to something that actually plays really well with renewables. And so instead of being a detriment and a challenge, it's something that can help the administration to see its commitment to renewables, because it is the base load that can fluctuate to accommodate the renewables quite flexibly and quite easily. And that has to do with the fact that instead of having solid fuel rods that are stuck in place, it's a liquid fuel. And so it's free to free mix and change concentrations and equalize. And so even if you're raising and lowering the power level, you don't have these localized hot spots and cold spots, high concentration, low concentration spots that you do in solid fuel. So it load follows really, really well.
Doesn't small plants and distributive models though change that base power issue? And that, like, if a group was a blockchain factory and they said, okay, we're going to go build a very small plant, and they're utilizing that plant during the day or during certain hours when they need it, and they end up having excess power, they're going to try to feed that back into the grid, and they're going to try to get paid for it. Well, that's what happens in oftentimes cases with solar or with other types of energy. There's a feedback for it, and you're getting paid. You can pay a different price for a peak power when it's coming on versus a base power load. So does the distributed small modules change that overall formula that says that all solar, or excuse me, that all nuclear must be a base load?
It does. It does to a large degree. And you brought up a good case that another form of load following is alternative use, right? With the data centers, they're going to use it and then sell it accordingly as the price on the market goes up for that electricity. They can sell it from their little plant. And having small also helps us, because now you have a bunch of little plants where you can divide up the production among each plant to one of those different sources. And so it's almost like having small and salt reactors is a two-tier or a double layer approach to this problem, where you have the distributed power, where, as you mentioned, you can reallocate the resources to other uses, and you also have the ability mechanically to load follow, and no longer are you constrained by trying to get as much money out of the operation as you can, because the cost is lower for these micro reactors, and you didn't pay for 1,000 gigawatts when you only needed 10, and so you have the flexibility economically to not run them full power. But really, you'd want to do that anyways and use that for other things like your data centers, like your desalination, et cetera, et cetera. And so you have both organizational and technical capability for load following that makes it a really robust companion to renewables.
So I'd like to ask some questions on the supply chain, just so I can have a better understanding of the challenges that exist there. And I'd start with the raw material. My understanding is that most of the raw material today is made in Russia and Southeast Asia, although we have the ability, I think, in Montana and Saskatchewan, Canada, to be able to pull these materials out. However, I don't know if we've even started trying to mine that material, or if there's any infrastructure in place to be able to do that. And certainly we're having challenges getting that from Russia today. Can you start by telling us about the raw material itself, how we're able to harvest it, what we need to do to be able to package it? Give us a better understanding of that component.
Sure. So when we talk nuclear fuel, it really right now all comes from uranium. And there's, as you mentioned, lots of uranium in the western United States. In fact, in Utah, if you go down to Moab or Zions or any of those places, there are a lot of mines where we pulled a lot of uranium out. When we pull uranium out of the ground, it turns out that 99.3% of it is an isotope called uranium-238. That is the isotope that does not fission or generate this electricity. The other 0.7% of what we pull out of the ground is uranium-235, and that is the isotope that splits. So most of the uranium that we pull out of the ground won't split and is not useful for fuel. And so what we have to do is we have to take that uranium that comes in the form of what they call yellow cake. It's U3O8, so it's an oxide of uranium. It's yellow. It literally looks like that cake mix that you get in a box. And so I have to tell my students, don't lick this. It's not cake. But it's... we process that. We pull out
Betty Crocker on the front or whatever.
right. So we process that. We pull out the impurities, and actually, it ends up looking like this. It ends up looking like a black powder. I don't know if you guys can see that very well, but that's U3O8 that's been purified. Once we've done that, then we have to convert it to a gas and send it to a facility to spin it in centrifuges where we can pull out the 238 and keep the 235 and concentrate that 235 and increase the fraction from 0.7% up to about 5%. They call that enrichment. And once it's enriched as a gas, then we convert it to the type that we use in the reactors, either uranium metal, uranium zirconium, uranium oxide, and that is what we can then convert to uranium fuel. Well, we used to be able to do all of that and have facilities and mines to do all of that. But it turned out that when we had a downturn in nuclear in the 80s and 90s, we found out that it was a lot cheaper to have Russia take care of that for us. And so we let Russia do the reprocessing, the enrichment and the processing, and we outsourced that all to Russia.
Sounds similar to the Germans on the
right.
issue of oil or
That's
natural
right.
gas.
That's right. That's exactly right. And so it's not that we didn't have the capabilities, but most of that industry died in the U.S. There are a few holdouts. For example, there is a mill down in southern Utah in Blanding called the White Mesa facility, and they still have the capacity and the license to process and clean up that uranium. Their main product is now shifted to rare earth elements and vanadium, et cetera, but they do have the capacity to process the uranium. And in fact, they have as side streams some uranium that they produce each year. And we have a couple of conversion/enrichment plants, but the licensing and the infrastructure is limited, and we do not have enough space, licensing, or infrastructure in order to produce our commercial amounts of uranium at home. And that's in essence the problem we've run into, is the war in Russia, straining relationships, and the tensions that come from supply from Russia has resulted in us needing that uranium and committing that we're not going to get as much uranium from Russia, which means we don't have a supply. And so the U.S. is aware of this, and the administration has been putting in place processes and protocols and goals and funding in order to expand our enrichment, our processing, and our mining, but it's slow moving. To get the licensing, as I mentioned, that long process just to get the higher enriched uranium or the higher amounts of uranium enrichment is 10 years. And so they're talking 10 years before Bill Gates's reactor can get the fuel it needs because of that bottleneck, because of the lack of commercial development of the supply chain. Now, when it comes to the other pieces of the reactor, a lot of the components are just nickel steels, incolloy, etc., and those things are available. But as we expand that power and that production of nuclear, we're going to need larger sources, and we're going to need manufacturing capabilities, which we don't currently have in the U.S. As an example, the Westinghouse AP1000 reactor required one of the world's largest single forging to contain that core. And the only places you could do that were internationally, in places like Japan or other places where we've outsourced construction to. And so there will be some growing pains, not just on the fuel side, but on the fabrication side as we seek to scale that up. I mentioned also, as an aside, thorium as being a really nice fuel alternative because you don't make any transuranics. And we have so much thorium that we could actually power the entire world, including all of this ramp up of scale for data processing, for 100,000 years just on our known surface deposits of thorium. That's how much power we have latent in this thorium. The challenge is there's no supply chain right now to get that, to mine it, to process it, to develop it, and to put it in the fuel. And when we proposed that to the US government, they said, nope, one major lift at a time. We're not going to worry about thorium. We're going to work on getting new reactors first, and then we'll talk about thorium.
How about transportation? Once you enrich this, I guess, to the 20% level, are there safety risks? Do you have to have a different, I mean, I can't imagine you're just loading them up in the back of a pickup truck. What's the process that people have to go through to be able to do the transport?
So if it's fresh fuel, it's actually not that challenging. We have certain packaging that we put it in to protect people, because fresh fuel, natural uranium, actually has a relatively low radiation level. It is radioactive, but it's not quite problematic. And in fact, that's kind of the safe baseline that we give to people, is once it's back to background levels of uranium radiation, then it's considered fairly safe. So it's actually not terribly rigorous. There are permissions that you need. There are protocols you have to follow, but they're well established. This happens regularly in the US as we refresh and refuel the various reactors. The challenge is on the backside. Once you've started splitting uranium, again, you've made so many of these byproducts that it gets really radioactive, and that's where it's a challenge. And that level for example, just the Idaho National Lab transferring spent fuel from one location to another along its roads, they have to shut down roads, they have to pay for permissions, they have to do it in the middle of the night. There's a huge protocol and process because the level of radiation has gone up once you've started processing or using that fuel. But for the fresh fuel, it's actually not challenging. So getting fresh fuel out to different places happens regularly, and it's a pretty standardized process that has a very low risk.
This has been such a fascinating conversation. Um, as a political economist, this problem of getting nuclear approved or seeing progress on this reminds me of a classic political economy problem where the benefits of something would be incredibly widely distributed. I don't think that most Americans actually understand how lucky they are to have affordable energy on the one hand, that energy is much more affordable here than in other countries. I know this very well because I came from New Zealand, where I think we have some of the highest consumer energy prices in the world. And I also lived for a long time in Germany, where, as you know, they pay some of the highest consumer prices to basically to subsidize renewables, while at the same time maintaining their industrial competitiveness. A lot of the industry wasn't paying what the consumers were paying. But Americans, I don't think, understand how lucky they have cheap energy and how much better off they would be if energy was extremely cheap. The sort of the prospect of a energy abundant society, I think almost people don't really even understand what that would mean and how much better off everyone would be if that happened. So the benefits are very widely distributed, but there's a very small number of people who are resisting this or blocking it. It sounds like mostly regulators, etc. But then who are the powerful champions of this moving ahead, right? So normally in political economy, you've got a big number of winners or losers, and then a small number of winners or losers that are really making the policy, right? You know, a classic example is in Europe, food prices are really high. Everyone pays high food prices, and the farmers benefit because they get the subsidies, right? Small group benefits, big group pays the cost. Who's the small group in energy that could or is trying to lobby for this to be made easier, for this energy abundance to sort of move into reality?
Great question. And from what I've seen, it's the small group, large pockets. Bill Gates is a great example of this, right? He's got the big money, he's got the big backing, and they are working with Southern Company to try and modify the regulatory environment / to make it something that is negotiable. So I would say there's actually two schools of thought on this regulatory barrier. And one is what you brought up, is a small group that has the financial and political capital to make a change. And it's a thankless job, and it is awful work. And the first attempt, the NRC came up with something even worse than they originally had for their licensing pathway. And so there's the siloed bureaucracy of regulators that is part of the challenge. There's another pathway to take, and that's the tack that we are taking because we lack that political capital and we don't have the will to wait the 20, 30 years it may take. And that is to innovate within the current regulatory environment, to use that regulatory environment to their advantage. So as an example, the Nuclear Regulatory Commission is under a lot of stress from the US Congress because these medical isotopes that I mentioned are not produced domestically. And back in 2007, both reactors, Chalk River in Canada and Energy in the Netherlands, shut down for extended maintenance. And we had no medical isotopes coming in because they decay after a few weeks. So they have to continually replenish the supply. We had no medical isotopes coming in, and we had a shortage and couldn't perform these diagnostic procedures. And so in 2012, Congress passed the American Isotope Act that says we need a domestic source within 7 years in order to support domestic radioisotope production. Well, it's now 12 years later, and we still don't have a domestic source. So Congress has been putting pressure on the NRC to come up with a domestic source. And back in 2020, right in the COVID period, the NRC released a public statement saying that if anybody had a reactor capable of making medical grade radioisotopes, they would fast track the licensing process and license it within 2 years. Now, I have my strong skepticism about the validity and the capacity of that licensing to be only 2 years. But nonetheless, those kind of statements and those kind of efforts mean that there is a pathway, even in the current regulatory framework, that you could get something licensed. And that's I'd say a big portion, maybe 60-70% of our innovation here is not just the technical, but the licensing innovation, so that with the current framework, we can move forward and license that. Then on the other side, you have TerraPower, you have Southern Company, you have Oklo, you have Kairos, you have these other great big companies that have lots of money, deep pockets, that are working through the political pathway to try and make that change and affect that innovation of the licensing. But even with that capital and with that power, because of the inherent fear and the reputation of nuclear as scary and dangerous that made its way into the licensing itself, I suspect that's going to be a long lead pathway, which is why we're choosing to try and work with the constraints to make it work faster.
Right. In my experience in the regulatory world, by the way, my experience in the regulatory world was that it was always incumbents that were the supporters of regulations. It wasn't just government, it was the incumbents. But to me, there are 4 areas that are important in regulations, and I'd like to know your comments on each one of them. I'll pull them together so you can answer them collectively. The first one is this idea of regulatory capture, the idea that you have an incumbent that wants to keep other people out of the business, and they've already created a type of product or a certain brand of product, and they don't want to see you move away from it. The second one, though, and I think this is way underestimated, it's the funding for the organizational capacity to be able to process permits. Now that's less clandestine and maybe less interesting, but you need money to be able to make these organizations work, and they need people. That takes me to the third issue. In your field, I would imagine, in other fields, it's hard to get the talent to do it because they're competing with the private sector. And so you end up getting a person who goes into the government on the regulatory side who is way underneath the technical experts that are on the outside, which can have all different types of consequences. But in your area, nuclear physicists, how are we doing on educating people in that science so that we're pulling more people into the field to make certain that we have the capacity that we need? And then the last issue is, in my experience, is that anytime you have something that people are afraid of at the political level, the easy answer is no. And so trying to make certain that your political leaders have an education and an understanding of what Henry was talking about, the incredible benefits that we gain from cutting the cost of our energy in half. And Henry, I'm going to ask you to talk about what you think those benefits actually are. But before that, the idea that the political realm, you have to get that side of it on your side. Where are we in the regulatory process on those issues? And are all 4 of those an issue today?
Yeah, I think you've nailed it right on. In fact, one that people often miss is that second one. So all 4 of those do apply. And for the first one, it really is inadvertent, I think. I don't think there was malicious intent to locking in the single technology, but now we're to the point where the only reactor they know how to license is light water reactors. And we have decades of legal precedents to that effect. So they're very adept at knowing what they want to do. When it comes to any other kind of reactor, they don't have the experience, and they simply say, we don't know, we're sorry. When it comes to the funding, that is a big challenge. Now, the NRC is unique in that all of their funding comes from the applicants. They actually charge applicants, I think it's up to $300 per head per hour to work on licensing their reactor. So the funding comes from the applicant, which is, we'll just say that there's all kinds of problems inherent in that to begin with. But the other challenge is what you mentioned of expertise. They don't have the expertise to look at these other reactors. In fact, I've had different groups from the NRC call me multiple times and say, hey, what students do you have available? We need people that know molten salt. We need people that know thorium. We need them here. And so I end up sending students to the NRC so they can build the expertise for these advanced reactors. And they recognize the lack of resources that they have relative to the amount of applicants they see coming in the pipeline. And they have chosen a variety of ways to address those concerns. Namely, if you have a customer already, you receive preferential licensing resources. If you have more of your design completed, you receive preferential licensing focus, et cetera. And so they do have an awareness of that challenge of lack of resources and lack of funding, but really it's more training than funding, and they have ways to try and address it. But the demand for those licensing resources relative to the timeline of getting a license are just completely mismatched. And so that will be probably the biggest challenge for a lot of these people trying to get licensing efforts, is whoever starts and gets that first commitment of resources is likely going to be the only one to have what they need in terms of regulatory resources for some time. And so there's almost a barrier to entry just of being first to the regulator. And some have gone quickly. For example, Oklo went to the regulator last year, but their license and their pre-work was insufficient, such that the NRC simply said no. Usually they say, hey, come back and answer these questions. This time they just said, nope, we reject that. And so those issues are going to be a challenge. And what I've seen, thankfully, is that with the current energy environment, there's an interest in nuclear. And so people are willing to talk about it. I think it's a combination of the people who are most scared of it have, quite frankly, aged out, right? The group that was having constant bomb drills and hiding under their desks and being told about the threat from Russia have moved out of these capacities. So it's a younger generation that doesn't have that same fear. And B, the recognition that we have a power crisis very quickly coming down the pipeline if we don't make some kind of change or implement something that's going to be workable. And those things I've seen have worked on both potential employees, i.e. students. We have a huge amount of interest here. That's actually why BYU requested that I come teach from Westinghouse. Is they had maybe a third of their students requesting nuclear engineering, and they didn't have a program. So they reached out to me as a graduate of the chemical engineering department and said, hey, can you come here and start building nuclear research and nuclear expertise and teaching?
Wow.
And also an interest in politicians and leaders and government incumbents, where I've had a lot of opportunity to just explain simply how nuclear works. Just like this conversation here, have this conversation. And most of the time they walk away saying, hey, that's not what I thought. This is really promising. But it really is a massive education effort where we're overcoming some of the challenges and fear that was in the past. And all of those things come together where we're getting new people going into the industry and to the regulator. We're getting education out so that when you have public comment, because nuclear is unique in that in order to get a license, you actually have to have mandatory public comment sessions where people will fly in from all over the world to talk about how awful nuclear is at these public comment sessions, right? And so having that education level raised helps not just with the regulatory and the workforce, but also with the public, because then there'll be less opposition during that licensing portion that requires public comment. And so all of those things need to happen. I think they're astute observations to the challenges of regulatory space. And I think that the awareness is such that people are working on that, but there's a momentum that needs to be built up and time of education that has to take place, as well as resources that have to be dedicated to overcome those challenges.
Comment that you made on what we call enterprise accounts. In government, sometimes you'll say, look, I want this department to be completely self-sufficient, so I want to charge fees to be able to make that work. But that works well in some industries. As an example, an airport, it's perfect. You have landing fees, the plane lands, and then when the plane gets done landing, they utilize your facilities, and then they take off again. It changes everything when you use it in the regulatory environment. And it begins with this. You are telling the people who are doing the inspections and who are doing the reviews, hey, the more things you find a way to charge for, the more money you're going to make. Exactly. And so that then begins to say, well, not only do I need to charge more money for this process, but I need to create more processes, because the more processes I have, the more revenue we're going to have, and the higher a likelihood I'm going to be able to have to save my job. If you want to make the nuclear industry take off, in my opinion, the central government ought to take a look, at least for a period of time, saying we're going to create the funding that's needed to be able to process these permits and remove the regulator from having a self-interest of slowing you actually down. Now, that doesn't mean that that you should be walking away from safety concerns and everything else. It's just remove the incentive to actually stop you by giving them the money, to have the resources, to have the people to be able to process permits, and to not be creating new ways to create more red tape that benefits them by having more revenue into their department or having them dependent upon it.
Absolutely. I couldn't agree more. And in fact, you're not the only one to think of this. Recently, a bill was introduced to waive NRC fees for a period of time. And that's a great step in the right direction. Unfortunately, the precedent and the buildup of 6 decades of having it the other way is still there and difficult to navigate. You never take anything away from a regulatory process, you only add. And so 6 decades of doing this, you've built up quite a pathway and rigmarole of licensing that just is difficult to clean up, even with the
You had
change now.
spoken to me when we were offline about alternative processes, though, possibly utilizing what the United States Navy has done to be able to permit the nuclear plants on their submarines. Can you talk about how that might work?
Right. So there's actually a couple different ways to license a reactor. The challenge is the NRC has sole authority on commercially operating reactors. So if you're making money on that reactor, then you have to go through the NRC. That being said, the other pathway is the DOE pathway. And a lot of the test reactors that were developed at Idaho, I don't know if you knew this, there was something like 53 reactors that were built and operated up at the Idaho National Lab. They are the hotbed of reactor development, ranging from salt to sodium to just about everything. And if you are not going to commercialize the reactor, you can choose this DOE pathway. That's what the Navy chose, Department of Energy licensing pathway. It doesn't have the same financial challenge or, shall we say, legal precedent that the NRC pathway has. So it tends to be shorter, cheaper, but similar in scope. Both are aimed to make safe nuclear that won't have these large accidents, nuclear that will result in minimum possible deaths per terawatt hour, which is what has made the nuclear so safe. But it does so without some of the incentivization that you mentioned and without some of the other challenges of this long drawn out process, such that they've gone through a probably 4 or 5 year process, I believe, to license a reactor called Marvel. And it has gone really well and is now pending that final license step via the DOE pathway. Now, again, a DOE reactor can be used for subs, it can be used for experiments, it cannot be used for financial. However, there's enough similarity, we hope, in the process that if you were to license with the DOE process, translating over to the NRC license should be simpler and easier. I say should because, again, the lack of expertise and the lack of manpower may make that still an insurmountable challenge. But we are pretty confident that if we have a license with the DOE, translation to an NRC license should go much smoother and take a significantly shorter time.
Henry, I'd like to hear more from you on what you brought up a moment ago, because I think that's a point that we should be making over and over again, which is the significant benefits that come to society with cheaper energy.
Yeah, for me, actually, high energy costs are like a regressive tax, meaning it's a tax on poor people. Energy is like food. You need it to survive. And regardless of your income, you have to spend a certain amount on energy, just like you do on food. Whereas rich people, they don't spend 10 times as much on energy as a poor person, even if their income is 10 times as much. They don't spend 10 times as much on food, even if their income is 10 times as much. So if you have high energy costs, you're imposing a much larger financial burden on working and poor people than on the rich. And so to me, high energy costs are a regressive tax on working people. And it means that they can't afford, or they have to scrimp and save on really basic things like heating and cooling their homes. That leads to people getting things like asthma in poor parts of the country. It leads to things like heat deaths in hot parts of the country. It also has all sorts of knock-on effects, and obviously the costs on absolutely everything in the supermarket or whatever. It all depends on energy prices, and also employers all use energy as well. And so they're going to have less money to expand to hire more people as energy costs go up. So I think I get really frustrated when I hear these debates around energy focused exclusively on carbon emissions, which to me are one part of a global problem of global warming, whereas high energy costs have real costs now that are unequally distributed on working people. And I find it extremely frustrating that the debate around energy has been so hijacked by this climate change issue, which is an important one, but it's a relatively remote one for people that are struggling to cool their homes in Arizona or heat their homes in Minnesota or pay for the gas for their pickup truck to drive to work. So I'll conclude my rant with that, Paul, but I get a little hot under the collar with these sorts of issues that affect real people.
And I'm always amazed when Henry thinks more about poor people than me, but because I tend to go to the economic development side of it, which is, as in a community, as a mayor, when you're trying to make a community grow, you really do have to look at all the different infrastructure needs that are there. What is so different today that this generation of leaders is facing than mine? Mine was water was at the top, then sewer expansion, road expansions, and our utility companies were able to keep up because the economy, while it was growing with the same types of industry. I think we have to pay really close attention to the types of industries that are now growing, that are employing people, that are creating a massive amounts of wealth for communities and improving our quality of life. It is things like blockchain technologies and AI technologies and driverless vehicles and electric vehicles. But those things are going to have a much greater demand for energy. And if we don't keep up with it, the answer, quite simply, is we won't be developing them. They will be limited to what they can do.
Will be
Matthew,
Germany. We'll lose our manufacturing capacity. We'll lose our competitive
Right.
advantage
uh,
over swathes of industry. Will be Germany. And
don't
even the
take that for
Germans don't want to
granted,
be
Henry.
Germany
Talk
right now.
about what that means. Talk about what's happening in Germany today, because I think it's worthwhile to spend a moment on that.
Well, they shut down their nuclear reactors in the wake of the Fukushima disaster, despite their nuclear reactors having absolutely no similarities to the position or the problems that the Fukushima reactor had. They then based their entire manufacturing economy, which was extremely strong. The German wealth of Germany is based on the export of very high value added industrial products like machine tools, expensive cars, expensive chemical products, highly specialized chemical products, and the export of those things to places like China and the US and Japan. And then, of course, the Russia Ukraine war came and they were cut off from the cheap gas supplies from Russia, which were what they were using for energy to manufacture all those things. And now the economy is in free fall. They have no idea how they're going to replace those energy sources to be able to continue this economic model that has led to the prosperity of Germany now, for 70 years since the end of the war. And the crucial element here is energy. And they have decided that they're going to solve all their problems with renewables, and they're investing billions and billions of dollars to try and conserve energy, to insulate homes, to build new energy lines from the north to the south, to be able to move solar energy north when the sun is shining in the south, and wind energy south when the wind is blowing in the north. But all this is taking way too long. The German big industrial giants are building factories in China, they're building factories in the United States, they're canceling plans to build factories in Germany. And the Germany's material sort of base of its economy is really fundamentally threatened by their neglect of just realities when it comes to energy production and distribution. And I think it's a real lesson for the rest of the developed world, and especially America, to just be realistic and clear headed about what this issue means, and that you cannot just decide that you're going to decouple from fossil fuels or from nuclear. There are realities that have a say in how that decision plays itself out that could be really devastating for your economy.
Right. And building on
Matthew?
both of those points, when we talk about Germany, it is a great object lesson, because when we talk about a 2 to 10 time increase in power production in the US, there is no single power production that has the supply chain or the capacity to provide that. We really need all of the above. And with people saying only renewables, we're talking about sending us to a pathway even more dramatically detrimental than Germany. We really need fossil, we need renewables, we need nuclear, we need it all, because 2 to 10 times increase of our current power production is just an enormous amount of electricity. And if we don't use everything we have, no one pathway will have enough bandwidth or capacity to supply it all.
So, in your industry by itself, there's going to be, I think, a great capacity for new jobs as well as new investments. I'm interested in how the industry is doing today on being able to raise capital, the process that they're going through. What opportunities do you see that will exist for people who are looking to invest in your company or in other companies?
Yeah, great question. So there's been a lot of resurgent interest in investment in nuclear. We're seeing this from the VC level all the way down to the angel investor level. And this is demonstrated by the fact that there's half a dozen to a dozen new startups that are getting capital to move things forward. Oklo is a great example. They just had their SPAC in order to get the funding to go through the licensing process and to build their small micro sodium reactors. And Bill Gates is kind of a different story because he has his own deep pockets, but he went to the government and said, I'm putting $1 billion in. What are you going to put in? And was able to get government support for developing this. And even on the smaller level, for example, our company, there's a lot of opportunity for angel investors or even the casual investor to put in money to be a part of the solution. And then there's further things that will need to be done to leverage that small funding into larger VC funding. The biggest challenge we've seen so far in the nuclear industry with VC funding is the timescales. A lot of VCs, particularly after the dot-com and information booms and with blockchain and other things being so lucrative on such a short time frame, talking about, hey, invest now and maybe 10 to 15 years from now you'll have massive returns is a difficult sell. And so there are groups that are putting together VC firms that are focused on longer term projects, but there are more companies that would demand those services than there are VC services to provide that. And so there have been really clever and creative solutions. Let me use NuScale as an example. They developed a process where they had a power purchase agreement, and they went to various municipalities in Utah and said, hey, we're building a reactor that's a test reactor in Idaho. We're going to get that license with the NRC. Will you buy our power in advance? And then here is a prorated cost schedule so that you can pay some money up front to support us and have less fees later on, and so on and so forth. So basically, groups will secure a spot in line to get power. And the motivation there is a certainty of receiving electricity based on the issues that Henry mentioned is valuable enough that they pay an upfront premium that's relatively small for these municipalities, but that would guarantee them electricity in the future. And that's a strong motivation. And so you see structures like this that will provide capital to startup companies in return for power in the future. So there's a lot of options and opportunities there. And a lot of companies are getting very creative because it's such a long runway time-wise and because it's a large ask in terms of CapEx.
All right, so give me an idea on time frame, and I want to put an assumption into this. Let's just say that we were able to truly engage the political environment so that they began to dramatically reduce down the regulatory time in all of the different areas to a reasonable time frame, a time frame that should be utilized to be able to process these. Not being a decade, but maybe 2 or 3 year period of time for processing. When you start looking at the challenges on transportation, the challenges on harvesting the product, on manufacturing the product, as well as creating the facilities, when do you really believe that we begin to see these types of facilities being produced and placed out there on a beta standpoint? And at what point do we actually get to moving it to scale?
So if we were to, if I understand your question right, you're talking about eliminating or at least reducing to reasonable amounts the barrier to entry of the long licensing process. Is that correct?
Exactly, because I think if you don't pull, if we're not able to fix that, this challenge becomes almost a hurdle that you almost can't get over.
Right.
But that's a man-made problem. It is directly a man-made problem that has created a lengthy process based upon building a facility like Palo Verde. And it to me, that just doesn't line up with the same regulatory process that you should have for building something that is a molten salt facility that is distributed, that is a small facilities, and that is dramatically safer. But saying that, I understand if you don't have the political will, the regulators are going to say, well, we'll deal with that problem tomorrow because that's
Right.
tomorrow's problem.
That's right.
So if assuming that problem got fixed, and my guess is you guys are optimistic about being able to fix those problems, or I would be
At
doubtful
least to
you'd be
navigate
getting
them
much money
cleverly.
put into it. Right. So with that problem being taken care of, knowing all the other supply chain issues that are there, when do we actually get companies like yours putting a beta out there where we can point to the facility that's working? And when do we actually get to them being able to be built at scale? I know that's a guess, but
Well, let me give this caveat that it really depends on how the company is addressing those issues. I would say if the company is savvy and if they have the capacity to navigate some of those issues cleverly, then you could see some of these reactors beta scale in as short as 3 years. Scaled up
Wow.
version in as short as 5 years. Again, because the licensing is that
Okay,
barrier to
that
entry.
is
Let me
much
give
faster than I thought.
Right. Well, let me give an example. We talked about the fuel, and the fuel is difficult to get in. It'll be 10 years before the fuel comes, and Bill Gates is subject to that. Well, we at our company specifically decided early on, 5 years ago, that we were going to use the same fuel that the reactors today use, the light water reactors. We're going to use the same enrichment, same supply chain because it was off the shelf and ready. Well, we're now the only advanced reactor company that is using the off the shelf fuel. So when we go to these people like the Idaho National Lab, they say, well, you have these 3 people ahead of you in line, but they don't have fuel, so we'll put you in the front now, right? And so if you're clever and you are able to foresee these challenges, I could see reasonably that 3 to 5 years you would have beta / scaled up production of these. The real uncertainty there is the licensing. Now, some companies are better at addressing these issues than others. Some have decided with the force of their finances, they're just going to bludgeon through that. And I hate to be crass, but that's kind of what TerraPower is doing. They have Bill Gates and big backing, and they're the ones who are trying to go the political change route, and they're just kind of pushing their way through with a lot of government support. But if you have people that are really being clever about this and are able to overcome that licensing, if the licensing was reduced to a reasonable amount, they could have these within 3 to 5 years. That really is why we don't see advanced nuclear. Is only 2 companies have gotten that license, NuScale and Westinghouse. Westinghouse went bankrupt, and NuScale is really struggling to maintain customers because their price has gotten so high.
That's terrific. Henry, I'll give you the last comment and question.
Oh man, high pressure. Matthew, I'd just like to thank you first of all for coming on the show. This has been really enlightening. Still have a lot of questions about energy and nuclear, but you've been able to answer a few of them. Maybe you could give us just a word or two on what life in America under conditions of energy abundance would look like.
Absolutely. It's great that you asked that question, because I actually just last year read a paper that just fascinated me. And what it was is a couple of scientists got together and looked at all of the technological advancements that have been produced over the last couple of decades, but that aren't seen or realized because of energy costs. And it was amazing. We're talking flying cars and vertical farming and desalination on levels where really the needs of the entire world are taken care of. And a lot of the wants and niceties of first world civilization are brought to fruition. The barrier to most of these technologies is energy. And they hypothesized in this paper that if energy were to go sub 2 cents per kilowatt hour, many of these really advanced sci-fi Back to the Future level technologies would actually become viable. And it's really just the energy limit. So I think I agree completely, Henry, with your statement that most Americans and even people throughout the world don't recognize the value that cheap energy brings. And my feeling is that if we can break through this manufactured man-made barrier of cheap energy and start producing cheap energy, we will see dramatic improvements in data processing, in quality of life, in global lifting of everyone else, to the point where I think it will be far more beneficial than just about any other policy we talked about to have this cheap energy freely and abundantly available in terms of quality of life and technology advancements.
That's wonderful. Matthew, Henry, thank you very much. And, New Frontiers is also part of an optimistic American program. I'd just like to say that you leave me very optimistic about our future. That's wonderful to see what's going on and what's taking place. It blows me away to know how much further ahead we are on this than I thought.
Great, thanks. It's been a pleasure to be with you guys. And anytime, if you have any other questions or comments or want to talk, I geek out about this all the time. My students know that they can miss an entire lecture or exam if they ask a question about a molten salt reactor. So anytime, happy to talk.
All right, thanks again. Henry, thank you.
Great, this was really great, thanks.
And we stand today on the edge of a new frontier, the frontier of unknown opportunities and perils. It holds out the promise of more sacrifice instead of more security. The new frontier is here.
You and I have a rendezvous with destiny. We'll preserve for our children this, the last best hope of man on earth, or we'll sentence them to take the last step into 1,000 years of darkness.